Osteotomies have been performed since thousands of years with mechanical methods for various purposes. For instance, at some point in time, it was believed that madness or evil could escape through a hole in the skull. Impressive results have been achieved with primitive, simple mechanical tools. For instance, by judging at the smooth edges in this craniotomy, it can be concluded that this patient had survived such a traumatic intervention. Early surgeons have achieved incredible results using tools to make round holes or a saw of this type to cut straight lines. These mechanical tools have evolved over the time, but have retained the archaic principle. The cutting principle of any saw is ingeniously simple. Sharpened teeth of any saw are pulled with force over a piece of wood, and the space between teeth, known as the kerf, accommodates the generated debris which emerges from the wood once the teeth is out of the wood. The saw is very efficient, but the friction generates a lot of heat, and the width of the teeth a lot of debris, and this happens with all kinds of cutting with mechanical methods. However, a saw can only make one type of cut, a straight line, and a drill can only make perfect round holes. Unfortunately, what works well for cutting wood does not work well for cutting bone in a live patient. Aside from the fact that wood processing machines typically produce a broader cutting width than the saw, they are invasive tools that cannot be retracted quickly or easily from the cutting medium and cannot adapt appropriately to the patient movement. When cutting bone, it is important to make thin cuts and that the bone is not overheated. Terminally damaged bone is known to slow down the healing process, and it is well known that when cutting with mechanical conventional method, there is a lot of heat brought to the system due to the friction of the blades. When looking at the microstructure of the bone, we can see an open, porous structure in which the blood and therefore the cells, which are needed to repair bone, can flow freely. With a conventional instrument, these channels are destroyed and blood flow is obstructed. This slows patient recovery. Optimally, the cutting process will create a cross-section that interlocks the bone pieces tongue and groove style, thereby creating primary stability at the cut site. This is not possible with straight cuts produced by a saw. To meet all this challenge is that we have invented the CARLO. CARLO stands for cold ablation robot-guided laser osteotome. With the laser osteotome, we can cut any desired shape. The cuts do not stress the tissue thermally and, as shown, can be performed in such a way that the cut pieces will achieve immediately stability when reassembled as an interlocking whole. The porous bone structure is not destroyed, and the blood vascularizes freely to bring cells to the damaged area. Bone remodeling can begin immediately after the cut has been made. There is no need to free the site of smudged debris. The cuts are thin and debris-free. The robot used is tactile and specifically designed for robot-human interaction. Patient motion is detected and compensated for. Since CARLO cuts with light, no physical instruments are inserted in the patient's body. This allows CARLO to react immediately, within a fraction of a second. CARLO was invented because I have a direct family member who had to undergo a complex osteotomy. I became convinced that must be some other way to make such operation using tools that have been invented thousands of years ago. My name is Alfredo Bruno, and I am the father of CARLO.